Imagine peering back through time, 13 billion years into the past, to an era when the universe was in its cosmic infancy. The light we see from that time has traveled across a truly unfathomable gulf, crossing the entire observable universe to reach us. And now, for the first time in human history, our technology has allowed us to catch a glimpse of one of the universe's earliest and most mysterious inhabitants, a black hole forming just 500 million years after the Big Bang. Today, we stand at the edge of a frontier once thought forever out of reach. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, has spotted something truly extraordinary. In the ancient depths of space, it has discovered a faint glowing speck, a little red dot, whose light has journeyed for eons. Scientists have named its home Kuiper's LRDZ9, a seemingly unassuming galaxy with a secret at its heart, the earliest confirmed black hole in the known universe. This is not just a story of a single black hole, but a window into the universe's turbulent childhood. To appreciate the magnitude of this discovery, let's step back and consider what it means to look so far into the past. When the light from Kuiper's LRDZ9 began its journey, our own solar system would not exist for another 9 billion years. There were no planets, no stars like our sun, and certainly no life. The cosmos was a wild, chaotic place, filled with swirling clouds of hydrogen and helium, and the very first structures assembling in the dark. Until recently, the earliest black holes we could detect were already well into their cosmic lives. Ancient, yes, but not primordial. But with the launch of the James Webb Space Telescope, our reach has extended farther than ever before. Equipped with exquisitely sensitive infrared sensors, JWST can pierce the cosmic fog and capture the faintest whispers of the early universe. The story began when astronomers noticed something unusual in the Webb's deep-field images, clusters of small, bright objects emitting a distinct reddish glow. These became known as little red dots, and they were unlike anything seen before. Not the sprawling spiral galaxies familiar from Hubble images, but compact, enigmatic, and luminous. Why were they so bright, if the early universe was supposed to be a place with few nascent stars? To solve this cosmic puzzle, scientists turned their instruments toward one little red dot in particular, Kuiper's LRDZ9. By analyzing the light from this distant galaxy, astronomers uncovered a telltale signature, a pattern of wavelengths produced when energetic gas spirals into the maw of a black hole. The evidence was unmistakable. Not only did Kuiper's LRDZ9 contain a black hole, but this black hole existed just 500 million years after the Big Bang, making it the earliest ever confirmed. The implications are staggering. Consider the scale. The black hole at the center of Kuiper's LRDZ9 is estimated to be 38 million times more massive than our Sun. For comparison, the supermassive black hole at the core of our own Milky Way, Sagittarius A star, is about 4 million solar masses, making this ancient black hole nearly 10 times larger. Even more astonishing, this object accounts for about 5% of the entire mass of stars in its host galaxy, a ratio far greater than what we see in modern galaxies. This finding challenges some of our most fundamental ideas about how black holes form and grow. In the cosmic timeline, 500 million years is a blink of an eye. For a black hole to reach such an immense size so quickly, it must have either started out incredibly massive or grown at a rate that defies our current models of galaxy and black hole evolution. The discovery has sent ripples through the astronomical community. How could black holes in the early universe have grown so rapidly? Did they form from the collapse of gigantic primordial stars, far larger than any we see today? Or did dense regions of gas in young galaxies collapse directly into black holes, bypassing the usual process of star formation altogether? Kuiper's LRDZ9 is now at the center of these debates, a cosmic Rosetta Stone, offering clues to mysteries that have endured for decades. The nature of the little red dots themselves is also under scrutiny. Their distinctive redness puzzled astronomers at first, but the answer may lie in the very environment of these ancient black holes. As matter falls into the black hole's gravitational grip, it heats up and radiates energy. But this light doesn't escape the galaxy unaltered. Instead, it must pass through thick, dense clouds of gas and dust, remnants of the primordial universe. As it does, the light is stretched to longer, redder wavelengths, a phenomenon known as redshift. What we see through the Webb's lenses is the signature glow of ancient matter being devoured by a cosmic monster. This process also hints at just how different the early universe was from what we see today. The galaxies housing these black holes were small, crowded, and chaotic, little red dots, rather than the grand spirals and ellipticals we're used to. Yet they burned brightly, powered by the gravitational engines at their center. If Kuiper's LRDZ9 is any indication, it's possible that black holes played a far larger role in shaping the first galaxies than we ever imagined. The discovery of Kuiper's LRDZ9 also sheds new light on one of astronomy's most enduring questions. How did supermassive black holes come to exist at the centers of galaxies, including our own? For years, astronomers believed this was a slow process, requiring billions of years of steady growth. But now, with evidence that massive black holes existed in the universe's earliest epochs, we must reconsider. Perhaps these objects formed quickly, in a cosmic growth spurt fueled by dense infalls of gas and rapid mergers. The findings from JWST's observations of Kuiper's LRDZ9 are only the beginning. As more little red dots are discovered and analyzed, scientists will piece together a new narrative of the universe's first billion years. Each new data point pushes the boundaries of our understanding, revealing just how much remains to be discovered. The techniques used to study Kuiper's LRDZ9 are themselves marvels of modern science. By breaking down the faint light from this distant galaxy into its component wavelengths, astronomers can read the chemical fingerprints and physical processes at work. Distinctive emission lines betray the presence of superheated gas swirling around a black hole, moving at incredible speeds and emitting energy across the electromagnetic spectrum. It is through this meticulous analysis that the earliest black hole was confirmed, providing a direct link to the cosmic dawn. This is the power of the James Webb Space Telescope, a machine designed not just to observe the universe, but to rewrite the story of its beginnings. Its infrared vision allows us to look deeper and farther than ever before, cutting through the cosmic haze to witness the birth of the first galaxies and the rise of the first black holes. Astronomers are now poised to answer questions that have lingered since the dawn of time. How many little red dots are there? Do all of them hide colossal black holes at their centers? What role did these ancient objects play in the formation of galaxies, stars, and eventually the building blocks of life itself? Each observation brings us closer to understanding the grand tapestry of cosmic evolution. As we contemplate the discovery of Kuiper's LRDZ9 and its ancient black hole, we are reminded of the vastness of the unknown. The early universe was a place of extremes, violent, energetic, and filled with surprises. With every new revelation, the cosmos becomes both more familiar and more mysterious.